Hello everyone, my name is Yassine Amoudi and I will be presenting a work on a quantum sub-Gaussian mean estimator. In this talk, I will present you an algorithm for solving the mean estimation problem over the results. In this problem, there is an unknown distribution D, which is obtained as output of some experiment. The mean of this distribution will be denoted by mu, and we'll assume that the variance is finite. The parameter n, which is an integer, corresponds to the number of times the experiment can be repeated. In the classical setting, this is the sample complexity, and it corresponds to the number of independent samples we obtain from the distribution D. In the quantum setting, I will explain later on what is a quantum experiment and what kind of information it provides about D. Now, given those n experiments, the goal is to obtain as output an estimate mu tilde, which is as close as possible to the mean mu. I will denote by epsilon n the error, which is the distance between mu and mu tilde. And the goal is to satisfy the inequality in red, which say that this distance is at most epsilon n with probability at least 1 minus delta. Delta is a failure probability which is fixed at the beginning. This problem has been studied quite a lot in the classical setting. And let me start with a simple case where the distribution has to be a Gaussian distribution. So of course, the parameter mu and sigma square, the variance, are unknown at the beginning. And in this case, the best estimator is just the empirical mean. We will just compute the average of the n samples you obtain. The error of this estimator is shown here, and it's the square root of the variance multiplied by log 1 over delta divided by the number of samples produced by the experiment. Now, in the more general case, where the distribution can be arbitrary, we'll say that an estimator is sub-Gaussian if it can achieve the same deviation bound as above, but for any distribution. Of course, the natural question is, do there exist any sub-Gaussian estimator? If we start with the empirical mean, it turns out not to be sub-Gaussian, and it performs worse on some non-Gaussian distribution. However, there does exist a sub-Gaussian estimator, and here are a few examples. Maybe the most well-known one is the median of means, but there are also other ones, such as the one obtained by Catonier or a recent one obtained by Lee and Valiant. This recent estimator is also optimal with respect to the constant hidden in the big O notation. This is for the classical setting. Now, if we move to the quantum setting, and even if I didn't define yet what was a quantum experiment, I can already give you what are the bounds which are known in this setup. So first, there is a result which has been shown by many different authors, which say that given an upper bound denoted by B on the largest element in the support of the distribution, we can achieve the following deviation bound, which is a product of B and log 1 over delta, divided by the number of quantum experiments we can perform. This error term is better than the classical one with respect to the dependence on n. However, the parameter B is sometimes larger than the variance. The second result, which is slightly better, is just a simple application of the well-known amplitude estimation algorithm. In this case, this new term, which is the square root of B and the mean mu, is smaller than the previous one, but it can still be larger than the variance of which shows up in a classical setting. A third result requires us to know as input an upper bound, capital sigma, on the standard deviation. In this case, it achieves the following bound, which can be better than the classical one when capital sigma is close to the standard deviation. Finally, a last result, which was also shown in previous work, requires as input an upper bound delta on the coefficient of variation, which is a ratio on sigma and mu. And again, it achieves a bound which can be better than the classical one if delta is sufficiently close to sigma over mu. So as you can see, the situation in the quantum setting is more contrasted than in the classical one. There is an improvement in terms of the dependence on n. However, the coefficients in red are sometimes worse than the variance in the classical setting. And we also need extra information about the input distribution, such as upper bound on some quantity that characterize D. The main result of our work is to unify those results and obtain a new quantum mean estimator, which achieves the following deviation bound, which is on the order of sigma multiplied by log 1 over delta, divided by the number of quantum experiments we can perform. This estimator has many advantages. So first, it doesn't require any prior knowledge about the input distribution. We don't need any upper bound on the variance or on the coefficient of variation. Secondly, it subsumes all previous quantum estimators I showed you on the previous slide. And it's also always better than a classical sub-Gaussian estimator. Okay, you can compare with the classical setting and see that the error term in the quantum one is always smaller. And finally, we show in our paper that it's also the optimal error bound you can obtain. This optimality proof is obtained by a lower bound, is obtained by a reduction from the quantum search problem. So for all of this reason, and because this estimator is the best you can hope for, we call it a quantum sub-Gaussian estimator. It's because it's kind of equivalent to the notion of classical sub-Gaussian estimator. So now let me move to the technical part of this presentation. And first, I will define what is the input model in the quantum setting. So there is some unknown distribution D, which corresponds to the distribution for which we want to estimate the mean mu. And let's say this distribution is represented by a probability vector P of X. The first possible input model, which has been considered by some previous work on other topics, consists of having n copies of a quantum state, sometimes called a Q sample, which is just a coherent encoding of the distribution D. However, in this simple model, it turns out that it is impossible to obtain any quantum speedup. In other words, the best you can do in this setting is to measure the quantum sample to obtain classical samples, and then to run any classical sub-Gaussian estimator. A second model, which is the one we are going to use in our work, is the following one. We assume that there is a unitary denoted by UD, which satisfies the following property. When you apply it on the all-zero state, it prepares a Q sample, potentially with some additional garbage register. Doesn't matter if there is such register or not. And what's important and different from the previous model is that this unitary can be applied as a black box. What I mean by that is one quantum experiment is defined as one application of either the unitary UD or its inverse, or the control version of those unitaries. So you can apply n times one of those unitaries on any state of your choice. This model is quite convenient because you can use subroutines such as Grover search or phase estimation on the unitary UD. And it's also maybe the most used model in previous work on estimating or testing statistics in the quantum setting. I have listed a few other papers that use similar input models. So now let me move to the description of the algorithm itself. And first, a simple observation, which is that one of the main reasons for which simple mean estimators, such as the empirical mean or amplitude estimation, are not optimal, is because those estimators are very sensitive to outliers. An outliers is just a value in the support of the distribution, which is much larger than the mean mu. A natural approach to improve the situation is to truncate the distribution at a certain truncation level T. By that, I mean that the outcome, which are larger than T, are just replaced with the value 0 or with any value which is smaller than T. Of course, by doing that, we are removing outliers, but we are also changing the shape of the distribution. And in particular, the mean is going to change, which means that one of the big questions is how to choose T in order not to change the distribution too much. Now, if you look at previous quantum mean estimators, and in particular, if you look at those previous three works, what you can see is the truncation level they choose is on the order of n times sigma, the standard deviation. This truncation level turns out to be pretty good because you can estimate quite efficiently the mean of the truncated distribution. However, it requires some prior knowledge about the input distribution. And this is why those previous works require some upper bound on the variance or on the coefficient of variation. Now, what we suggest to use in our work is to use a different truncation level, which is defined as follows. It is taken to be the quantile of the distribution D that satisfies the inequality in a range, which say that the probability of obtaining an element larger than T must be on the order of 1 over n squared. It turns out that such a quantile can be computed quite efficiently and without needing any prior knowledge about the input distribution. And in our paper, we describe a quantum algorithm that can estimate it by doing on the order of n quantum experiments. This algorithm is based on some simple adaptation of the quantum minimum finding algorithm. In comparison, if you want to compute this quantile classically with classical experiments, it would require you to use on the order of n squared classical samples. Now, for the second part of the algorithm, which consists on estimating the mean of the truncated distribution, I will make some simplifying assumption. So first, I will assume that the failure probability is chosen to be 1/3. Secondly, the distribution will be assumed to only take non-negative values. And finally, in the complexity bound, I will state the variance will be replaced with the second moment. In the paper, those assumptions are removed. Okay, so now for the algorithm, so we have the truncation level, which has been computed before. And what we do is we further split the domain of the distribution as follows. There will be on the order of log n intervals, where the first interval corresponds to all the values which are between 0 and t/n. The second interval corresponds to the values which are between t/n and 2t/n, and we continue like that by doubling the size of the interval each time. Then we estimate the expectation of the distribution restricted to each of those intervals, okay, which correspond to this quantity. And this quantity is estimated by the standard application of the amplitude estimation algorithm to the mean estimation problem. This estimation is also performed by using on the order of n quantum experiments. So we do that independently for each interval. We'll obtain a sequence of mean estimate, and we just take the sum of all of them. And above the threshold value, we just estimate this part of the distribution by the value 0. Now, if we compute the error bound, I will not go into too much detail, but the computation is pretty simple. You can show that for the part of the distribution which is below the truncation level, the error will be on the order of this quantity. And then for the part which is above the truncation level and which is not estimated, the error will be on the order of this second quantity. Now, one can show that the truncation level is always smaller than n times the square root of the second moment. And by definition, this probability is on the order of 1/n squared. So as a conclusion, the error that we are making by using this estimator is on the order of the square root of the second moment divided by n, which is exactly the bound we wanted to obtain. Okay, in practice, this second moment is replaced by sigma squared, which gives us sigma over n. So that's all for the technical part. And now I would like just to give you a few applications of this quantum sub-Gaussian estimator. And maybe the most natural application is for estimating expected values of observables. So in this case, the mean is the inner product between some state psi and some observable O, and the variance is also sometimes called the uncertainty. Now, in the quite common situation where this state psi is obtained as the output of some Hamiltonian simulation process, then the number of quantum experiments, this parameter n, will correspond to the number of runs of Hamiltonian simulation we are using. And so with n runs, we can obtain an estimate of mu that satisfies the error bound that I described before. The second important family of application is about Monte Carlo estimation, which includes problems such as estimating integrals, partition function, or application in mathematical finance. Okay, in those situations, the use of mean estimator is pretty much interesting. And there are quite a lot of other potential applications. Now, to conclude this talk, I would just like to recall what is the main result, which is obtained in this paper, which is a quantum mean estimator that achieves the bound in orange, and that should be compared to the best classical bound that one can obtain. And those kind of estimators, we call them sub-Gaussian. They are the optimal one that can be found. A few open questions. So a first open question would be to improve the dependence, would be to improve the hidden log factors in the quantum bound. I didn't talk about them, but they are log factors. A second interesting open question would be to generalize those kind of results to the multivariate setting where the distribution is defined over some multidimensional space. So there has been some recent work on some related question, which might be interesting to approach this question. And finally, I think that can be many other potential applications, and it's probably interesting to look at that. And with that, I thank you for your attention.